This video contains the solution to number 2 on the 2008 AP Calculus BC free response. We are using our calculator here, and when we see fit, we'll need it on some parts in this question. So let's see, we've got a table of values here, time in hours and L of t in people. This is the length of a line, how many people are in a line waiting for concert tickets. They want to sell at noon, which is time 0, and we're sold out within 9 hours, so that would be 9 p.m. Number of people waiting in line to purchase tickets at time t is modeled by a twice differentiable function. That just means we can do calculus, we don't have to worry about any funny business. L, that's this function, from time 0 to 9. Values of L of t at various times are shown in the table above. So let's see. 2a, I'm going to use the data in the table above to estimate the rate at which the number of people waiting in line was changing at 5:30. That's time 5.5. Right in between those. And show the computations that lead to your answer. Well, a rate is a slope, so the rate at which the number of people waiting, this is the number of people waiting in line function, so the rate of that is the derivative of that. So I think if I just have a table of values, I'm going to have to find a slope, and a pretty good estimate for time 5.5 would be the slope of the secant line connecting those 2 points. So let's do that. So 150, that's y minus y over t minus x if you want, but I should say L of t minus t over t, but it's just the slope here. 7 minus 4, and that gives me, what, 24 over 3, or 8. And the units would be, since we're finding slope, y over x, or L of t over t. That's peeps per hour. And that makes sense? Yeah, sure. It was increasing. The line got longer, so it was, the rate of change was positive, and it was approximately, or on average, 8 people per hour. All right, use a trapezoidal sum with 3 subintervals to estimate the average number of people waiting in line during the first 4 hours. It's from here to here, and there are 3 subintervals. They're not going to do anything weird there. There are 3, so they asked us to use 3. So the average number of people waiting in line, this is the function that's the number of people waiting in line. So average value is of a function is 1 over b minus a times the integral from a to b of whatever function. In this case, it's the L of t. Remember, don't get this confused with the integral of a derivative. It's not that. We actually want to know the average number of people of this function. So that means I need to find the trapezoidal sum and then divide by 4. That's how wide the interval is. So let's set that up. This trapezoid is 1 wide times the average of those 156 plus 120. I don't know why I put the 156 first. It's a strange thing to do. And then that trapezoid is 2 wide, and then the average of those 156 plus 176 over 2 plus this trapezoid is 1 wide. That's 176 plus 126 over 2. Take the average of these because we're saying the area of a trapezoid is like a rectangle with that width and the height of the average of the 2. So punching that all into our calculator, let's see, I already did that, and I got an answer of 155 people, approximately. Your answer should make sense. Does it? let's see, from here to here, does it make sense that the average number of people waiting in line was 155? Yeah, that looks about right. That looks good. If it was bigger or smaller than all of those numbers, then that couldn't possibly be an average. That's not the answer you'd get, by the way, if you just averaged those four numbers, and you would not get any credit for that, for doing that. Okay, so part C, from time 0 to 9, whole interval, what's the fewest number of times at which L prime of t must equal 0? And give a reason for your answer. Well, it's twice differentiable. That's actually important here. That means that it's a smooth curve. And let's see what it does. It increases up to here, and then it decreases, and then increases, and then decreases down to 0. So let's just make a little sketch of that. It increases, and then decreases to 126, then it increases to 150, and then decreases down to 0. Let's make sure we got that right. We got increasing up to here, decreasing, increasing, and then decreasing down to 0. All right, and they want to know what's the fewest number of times at which the derivative of this must equal 0, and give a reason for your answer. Well, it looks like 3 times, because LT is twice differentiable, which they told us. So those maximums and minimums, they can't just be like sharp corner. We could have, it's not just the maximums and minimums, it's the fact that it's twice differentiable, because we could have like a sharp corner, right? It could be like an absolute value kind of thing peeking out there. But they told us that it's twice differentiable. That means that it's a nice smooth curve, and that we can actually find the first and second derivatives of that function at any point. So all of the maximums and minimums must actually correspond to the derivative being equal to 0, not sharp corners. And last part, the rate at which tickets were sold from time 0 to 9, modeled by this function, tickets per hour. Based on that model, how many tickets were sold by 3 p.m. to the nearest whole number? Well, let's see. We want the total number of things, total number of tickets, and we've got a rate. So that sounds like an integral. Total number of tickets is equal to the integral from time, what do they want, from 0 to 3 p.m. of the rate function. And that's something that we're going to want to put in our calculator. And when you put that in your calculator, you should get 973 tickets. And please go ahead and put that in your calculator and make sure that you get that.